missed those golden first few moments, but that's okay. Yeah.
So, thank you for being here. And I'm Osmar Zaiane. I'm a computer scientist. I've been at the university for 20-something years. I'm also the director of the Alberta Machine Intelligence Institute, which is an institute specializing in machine learning and AI in general. On Tuesday, I gave you part 1 of my talk, Promises and Perils of Artificial Intelligence. And in that part 1, I talked about AI, the past and the present. Today, I'll be talking about, first, I'll start with examples that I couldn't give you on Tuesday. And then I'll talk a little bit more about some views towards the future. So before that, since Ashley wasn't here on Tuesday, I'm giving her a very brief summary of what we did. So I talked about the fact that artificial intelligence is not a new field. It has been around since the 50s. And in the beginning, they were trying to build some systems that can mimic the human intelligence. And they focus on games and things like that. But there was a disillusionment and people didn't believe in AI anymore, except some few believers who persisted. And in the 80s, we saw the emergence of a subfield of AI called machine learning. And machine learning focuses on, let's say, teaching a machine to do some task without being programmed for that particular task per se. We just program how to learn, and we provide examples, and it learns from those examples. So machine learning is a subfield of AI. And recently, so in the last decade, even less, there was a subfield within machine learning that emerged called deep learning, which is actually a rebranding of a technology that existed also from the 50s called artificial neural networks. And this subfield is now called deep learning. So what you need to remember is that deep learning is part of machine learning, which is part of AI. I also talked about the fact that, well, I tried to explain why this resurgence of AI today. I said that it was kind of dying at one point because people didn't believe in it. Now it's coming back. It's actually thanks to deep learning, among other things. But there were 3 factors that led to this resurgence. One is the abundance of data. We have way more data than we ever had before. We keep on collecting because it's cheap to collect and keep everything. We have also means to collect this data, electronic means that are automatically collecting stuff. You are doing things online and we collect stuff based on what you're doing. So that's one factor. Another factor is the high performance computing. Computers have evolved significantly, and I tried to illustrate that with some anecdotes. The computer on my watch is more powerful than the onboard computer of Voyager 1 and Voyager 2 that were sent in space, just to give you an idea. I mean, it's mind-boggling. The third factor is the improvements in the algorithms that we have. Among them is what we call deep learning, because now we can have sophisticated algorithms that can run on those sophisticated machines and can exploit the data that we have. So that is why. So without further ado, I'm going to talk about the examples of applications of machine learning in particular in the context of precision health. So just a reminder of what we discussed yesterday. What is machine learning? Machine learning, basically, you have different subfields, the supervised learning, unsupervised learning, reinforcement learning. Here I'm focusing on supervised learning, and I'll show you an example with reinforcement learning later. But what is supervised learning? Basically, you have data that is labeled, and an algorithm goes over that data that is labeled. The labels here are putting colors as an example. Each point here is a record, for example, and then you have features like a patient, you have the age, you have whatever, and the labels here could be, for example, the disease that they have. And you learn a model. That model is a predictive model, and then later you will use it to automatically label objects that have never been seen before. Okay. So where's the learning? The learning happens here, where I give examples, which is the experience, we call it training set. And based on that experience, the algorithm will build a label that can discriminate between the different classes. Okay. So how can we use that? And this is what I'll show you in precision health. Yeah, so one of the models could be, for example, a neural network. Okay, but there are many other paradigms. Okay, so what is precision health? Precision medicine refers to the tailoring of medical treatment to individual characteristics. Each person is different. Each patient is different. So medicine typically is personal, but the way we are operating today, actually, different people with the same symptoms, we treat them the same way. Okay. Even though here you can see this cohort here, you have different people representing the colors here, the meanings they have the different characteristics. Well, if they have the same disease, well, we'll give them the same treatment. So what we try to do with precision medicine is try to go towards individualized treatment. It's not always the case. Even if we can potentially group individuals into different cohorts and subpopulations, then we can give them, with populations that presenting differences, of course, then differences that distinguish them with respect to responsiveness of disease treatment, then we can give them, in that case, for the same disease, the same symptoms, we can give them different treatments. Okay. So that's also personalized medicine. I mean, the best case is when you personalize to the individual themselves. So when we talk about personalized medicine, often people think about genetics. So microarray data, SNPs, single nucleotide polymorphisms, genomics, metabolomics, microbiome, and so forth. But it's not necessarily always the case. You can also do personalized medicine using all sorts of information. I'll show you some examples. Okay, so personalization goes beyond just genetics and all sorts of omics. So how do we do this? Basically, I'll give you an example here. You have a new patient, and this patient, you have a record of that patient. So let's just some information here, put ... and you have values for these features. We call them features or variables or whatever. And you want to know, for example, if for this patient, a particular disease will reoccur or not. So you want to predict it. Prediction is also classification in our case. So what we do, we look at the history, other patients that, I mean, for whom we have the information whether the disease reoccurred or not. And this is what we try to predict. The reoccurrence is what we try to predict. And we have the same features from other patients, but different values, obviously, and you have many, many, many of those. So what we will do, we'll use this information to build a model that can classify yes and no here. These are the two classes, yes, no. We'll build a classifier or predictor. And once we learn to classify, we will use this classifier to predict for this patient whether, based on this information, it will reoccur or not. Okay, so the same idea can be used in many, many, many applications. So here's one application where we are trying to predict if a particular patient for the treatment for cancer, for example, an adjuvant treatment after chemo, we want to know what kind of hormonal therapy we can do, and that depends upon whether that patient is estrogen receptor positive or negative. And what we can do is we can look at the microarray data of previous patients for whom we know whether they are ER positive or ER negative. We will look at the gene expression. So this is, for example, the data. We can build a classifier. And then once we have that classifier, when we get the biopsy from the patient and we do microarray data from it, we extract the microarray data, we can pass it to the classifier, and the classifier will tell us, is it ER positive or ER negative? It happens that actually, and this has been published, this is work done here at U of A, it happens that this is actually more accurate than the current technique that we call immunohistochemistry, I believe, that is typically used. So it's very accurate. And once you have that, then you can prescribe, for example, taximofen or not for the adjuvant treatment after chemo. Same thing for the other hormones. So this is an example where machine learning can help us prescribe one treatment or the other based on a particular patient. And this same technique can be used in many, many, many other cases. For example, you can predict whether a patient will develop breast cancer or not. What is the likelihood? I mean, it's never 100%, but we are getting some also confidence level. Predictive breast cancer could reoccur or not. We can predict whether a transplant will be rejected or not, or will it be rejected with higher likelihood with this patient than the other patient. We can, for example, in the case of prostate cancer, predict the toxicity level for a radiotherapy for this patient or the other patient. We can predict the loss of muscle mass, decuxia, and we can use microarray data or SNPs. But it's not this is an example, the typical examples with genomics. We can also use other information, metabolomics. This is in the case of decuxia. Instead of checking the blood or biopsy or whatever, we could just use urine, and with nuclear magnetic resonance spectroscopy, we can extract information, and that information is given with labels to a classifier with many, many patients. And then later when we have a new patient, we can do the same thing, extract the information from the urine, and we can predict. Okay, so exactly the same here. We're building a classifier, and then the classifier will predict yes, no. And this can be done to do diagnostic, to do prognosis, to predict the best treatment, and so forth. Here's another example, completely different. This is in the case of diabetes type 1. So in the diabetes type 1, people don't have insulin, so they have to inject themselves insulin based on, normally based on their activity and what they eat. But the way it works today, you have the patient actually fills in a log like this, where they say, today this is what I did, and today this is how much I injected insulin. And once every 3 months or 6 months, sometimes they go to the doctor and say, well, here's my journal, here's what I did, and what should I do next? And then the doctor will say, oh, you can adjust the formula, so how much insulin you should inject yourself, or leave it as is. And then they come back after 6 months and do the same thing, which is very tedious and very complicated, and it's never perfect. So the idea is to use reinforcement learning, and the reinforcement learning algorithm will adjust the perfect dosage to inject based on the sugar level in the blood every day. So instead of waiting 6 months or 3 months to see the doctor to adjust this, it is adjusted using machine learning, using reinforcement learning. Reinforcement learning, remember, is the case of that agent that gets rewards and tries to maximize the rewards that it gets. um, and learns a policy. In this particular case, the actions are how much insulin to inject, and the reward would be positive if the sugar level is good, and it's negative if there's a hyperglycemia. So it learns to optimize that, and at the end you get something perfect. So this is also done here at U of A. Here's give you another example. So the previous example, I'm not using any genomics here, and this is another example where we're not using any genomics. This is the case, it's also work done here at U of A, this case of people injured and treated at the clinic of the Workers' Compensation Board. The goal is to treat them well and get them back to work as soon as possible, otherwise we waste time and money. So you want a quick treatment and the right treatment. But what happens typically is that after somebody is injured and we give a treatment, there's an evaluation, and the evaluation tells us whether we need a secondary treatment or this person can go back to work. And typically there is need for secondary treatment. After you do the secondary treatment, there's another evaluation, and you may iterate here until they are fine, and then they go back to work. Unfortunately, there's this iteration, and when you look at the history, all the patients that go through these clinics, there is an iteration here. It means that probably that secondary treatment that we gave wasn't the right one. We should have given a different one. There are different reasons why some treatments are given instead of others, but I won't go into those details. The point is that we were called upon to look into this problem. And what happens is that we looked at the cases where we didn't have long iterations, and we tried to learn from that. So how did we learn? Well, basically the evaluation, here's where the second step. So the evaluation is a questionnaire that the evaluator has to fill, asks questions, how do you feel this, how do you do that, and so forth. It's a long questionnaire. So that questionnaire is the input, and the output is which treatment to give for that particular case. And that's what we learned from the previous data that was relatively short. And we build a decision support system that predicts what is the best secondary treatment to give after the first evaluation. And indeed, we managed to demonstrate that on average, the treatment is way shorter than what was done by the humans in the past. Another example that I really love very much, and I like talking about it, that is using machine learning to help doctors, is the following. Because when you see an example like this one, people will say, there you go, machine learning is replacing doctors. We don't need the evaluator anymore. We don't need the doctor anymore. Actually, it's not true, because the evaluation is done by a specialist. This is a recommendation. And the recommendation, well, somebody has to make that decision. The decision maker is still the doctor, who will ask the decision support system, why did you recommend that? And if the reasons are good enough, then the doctor may follow that recommendation or may not, and may add something else. So the doctor is still in the loop, except that here we shorten the process, and so it's a tool that helps the doctor make the decisions. Here's the same kind of thing. So this is the case of brain cancer, and they have to do surgery here, either to cut the tumor or to bombard it with X-ray or whatever. Before the surgery, the doctor has to do a segmentation in 3D, okay, so in the volume. It's not a 2D image, it's you have a set of slices, I think 32 slices or something like that, and they have to segment it using a special tool to identify that particular area that needs to be cut. And this process is very tedious, it's very complicated. It takes about 30 minutes to do per patient. And if you ask two different doctors, they may not give you exactly the same segmentation. Even the same doctor in the morning and in the afternoon, or before or after taking a coffee, the segmentation may not be exactly the same. So it's a very difficult job. They do it and then they have to check it again and so forth. So the idea here was to take the successful segmentations in the past and use machine learning to learn how to do the segmentation. Again, people say, oh, there you go, you're replacing the doctor. No, it's not to replace the doctor, but it is to present something that is pre-segmented. So it's an initialization. The doctor, instead of starting from scratch, the doctor starts with something that is already pre-segmented, and they only spend 5 minutes to adjust it here and here and here, and it's done. So instead of spending 30 minutes, they spend 5 minutes. Okay, so again, this highlights the fact that AI is not about replacing people. AI is about building tools to help us do our job better. This is the case of medicine, but it's in other fields as well. Here's another interesting project that I'm working on. It's about detecting depression from text. There's a lot of people who are working on detecting emotions from camera, for example, if somebody's happy or sad or angry or whatever. We are looking at text because it's coming from speech, and speech is only arriving to us after being transcribed into text. So we only see the text, we don't even hear the sound, and we needed to detect signs of depression. So we developed, using machine learning and using labeled data that an expert told us this expresses happiness, this expresses anger, and so forth. We were able to create a classifier that finds the emotion that is expressed in the text. So using that, we were working on detecting depression or signs of depression, because if the emotion goes down and it stays down for a long time, for example, that could be a flag. Everybody has a roller coaster going up and down, but if it stays down too long, that's a bad sign. Anyways, we are also working on detecting other kinds of emotions, not just the typical ones like anger and love and sadness and surprise, but things like deception, feeling rejected, and so forth. These are special emotions that people with depression could have. And we have a recent paper that we published last year to show that this is actually quite effective at detecting depression just from the text. Okay. So very quickly, what we talked about here is that machine learning can be used in precision health. It's actually key, the key technology for precision health and precision medicine. Doing that, it's not just looking at genomics, it encompasses all sorts of data. I'll show you many examples. So this AI thing that we are talking about is literally transformative for not just medicine, but any sector of the economy. And I'm proud to say that the U of A is one of the top global leaders in AI in the world. There's still many challenges. It's not a done deal, and it's not a silver bullet to solve everything. So there's a lot of work to do for us researchers. And lately, there are many people who are alarmed by this AI. I don't think they understand very well AI. That's why they're alarmed. And it has to do with the fact that the wake-up call happened suddenly, and there's a drastic increase. There was this hype, and people got scared. But less and less today. So when they're alarmed, of course, they're saying, well, this is replacing us, we're losing all our jobs, and maybe it will eliminate us, so it's an existential threat. There are other concerns as well related to privacy, especially when we deal with medical data. Let me show you some slides that may scare you a little bit.
Dr. Kim, yeah, he's in class. May I ask a question before we move on?
Sure, yeah, by all means.
So, I mean, to build a tool like a classifier or a tool that would predict, for example, a recurrence of a disease or what medication would work for some sort of patients, what are the criteria should be, this tool to say this is a classifier or, a tool to predict recurrence of disease, or for example,
There's a person
something
there
like,
who
what are the
has your name.
criteria that should be available? I mean, I know there is so much of data to build that, but
Hello there.
criteria specialists
Yes, I did.
to build this tool.
I think Dr. Kim should mute his microphone.
This is, I mean, somebody asked for it in my.
Okay, well, he hasn't heard us saying that he should mute. But Khadija, you are talking about, so you're asking about criteria to decide whether it's a good classifier or not? Is that what you're saying?
No, I mean, even to build one.
Even to build one.
Yeah.
Great, thank you.
So actually, this question is a very good question, and I probably will cover it in the third part of the, so well, next week, basically on Tuesday.
So were you waiting to ask me something?
No, I
Kim, you're not muted.
Okay,
Oh, Kim, you are not muted.
I'm sorry.
So anyways, I'm answering the question to Khadija. So it is important to have data. Without data, you can't do any machine learning. And in addition to having data, you need to have data that is labeled. So somebody has to tell me this patient has cancer, this patient doesn't have cancer, this patient doesn't have cancer, this patient has cancer. So if I have enough data that is labeled like that, then I can build a classifier to distinguish between cancer and no cancer, the example of cancer, no cancer, but it can be any other things, okay? But that's not enough as well, because I can build a classifier that has very bad accuracy. So typically when you have the data, it is split into different parts and you learn only on one part. So let's say we split it into two. There's one part that is used for training and the other part is hidden. Once you build your classifier, you take that hidden, we call it holdout, you hold it out, you put it aside, you take that data and you use it for testing. What do you hide now? You hide the label, you give just the data to the classifier and see if the classifier can predict the same label as the label that you expected. And with that, you can calculate an accuracy. So once you have that accuracy, it reaches the level that is acceptable, then you say, I can deploy it.
Okay. What level of confidence should be in this kind of tools?
Okay, so that's a very good question. What is an acceptable accuracy? So if I am building a classifier that is recognizing what is spam and what is non-spam in my mailbox, if it makes some mistakes, it's not a big deal. So an accuracy of 80% is okay. It means I have some emails that are spam that is still coming and bugging me, and there are some emails that are not spam that will go to the spam folder. It's not a life and death. But if my classifier is deciding whether to turn off or turn on a power plant, the false positives, it means that I will turn off the power plant for nothing. And it cost me a lot of money to start it again. And even worse, the false negatives. I have something that is going to explode and I don't detect it and I don't turn off the power plant and it explodes. I have people who may die. So it's way more expensive. In that case, an accuracy of 80% is useless. I want a 99.99% accuracy. Okay, so answering that question, what accuracy is needed to deploy, it depends upon the application. It depends also about our capabilities. There are some applications where even the human beings, the specialists in that field, may not reach 70% or 80% accuracy. So even if I, as a computer, I generate a predictor that doesn't reach 99%, but I can predict better than the humans, then that's worth deploying. If you look at, for example, detecting breast cancer using mammograms, the humans make a lot of mistakes. Okay, so we're not at 99%. The humans still do about 12% error rate. So if you manage to build a classifier for mammograms that reaches 90%, that's already good. Okay, does it answer your question?
Yes, thank you.
Okay, cool. So now let me scare you a little bit. This is a representation of a DNA. It's not a real DNA, but this is how many big e-business see a customer. They talk about the DNA of the customer. So this is hypothetically speaking. I have an e-commerce site and I go there and then register. So I register, they ask me for my name, they ask me for my address because they will send me the stuff I'm buying. I'll give them that. They ask me my phone number. Okay, I'll give them that information. They even ask me for my birth date. Yeah, I'll give them that. Maybe they will send me something, a discount for my birthday or whatever. So I voluntarily give them that information. They even ask me where I was born and what's my profession, stuff like that. So I give them that information. They didn't steal it from me. I gave it to them. But I think that's all they know about me. That's fine. They can't hurt me with that. Then I start using the website. Okay, so what do I do? I buy things. So for example, I bought this watch. It's a waterproof watch. I also bought goggles. Ooh, they already know more about me. They know that I swim. Okay, I may, oops, here. I'm not using the right. So anyways, there's registration, then there's activity. Then I have other behaviors. I may review products. I didn't like this product. I like this product. I like this part of this product. I may reply to other comments that people have on the site. So that behavior gives them even more information about me. Mind you, when I did the purchase, I may have bought things that are not for me. I may have bought, for example, here a coffee machine because I'm going to offer it. I'm going to offer it as a present for the wedding of my student or something like that. They may think I drink coffee, but I don't drink coffee. There is noise in the data, but overall, they know quite a bit about me. Even when I do a search, I'm searching for a product. I didn't buy it. I didn't comment about it, but I'm just searching about it. And it tells them something about me. So here I search, for example, about home improvement. Aha, he's improving something in the house. So I could use that for ads, for example. I may start building friends in that site and we exchange information and that exchange can also give them more information. They don't stop there. So we talked about registration, activity, behavior, but they even go online, automatically search more about me. They know enough about me to do a search. And then when they search about me, they may find my friends. What do they like? What don't they like? What do I like on social media, for example? They can go and see on Twitter, what do I tweet about? They can even see where I went because there's geolocation for the social media. They know the places I visited. They even go on LinkedIn and see my colleagues. What do my colleagues do? What do they publish about? If you are on Foursquare or something like that, they also know how you move in the space you live in. Doing searches on search engines, they can find additional information like the YouTube channels I have, the Flickr images that I collect and share. On Wikipedia, did I actually edit pages on Wikipedia about politics or about places, about flowers or religion or whatever? They may even check the blogs, the news that I wrote and the text that I wrote and maybe extract emotions. So now they even know when I was happy, when I was sad, when I was angry about what. So you can imagine just for me, just one person, they collected enough information that they know more about me than my mother does. Why do they collect this data? Well, simple. It's very profitable. You can use it to target these people with advertisements that are effective, that they will buy things. I'm not going to send flyers that you will dump in the recycling bin. I will really target you with things that I know will influence you and you will buy. Okay, so it's very useful. And that's why they invest a lot of money to do this, and they do it. Now, if now I turn it around and say, well, this is not the DNA of a customer, but it's a DNA of a patient. So what do we have? We have some generic information about the patient. The gender, the name, the age, ethnicity. Maybe if we collect it in the US, they do, but not here, but we should. Actually, we have machine learning techniques to predict the ethnicity. There's information from the electronic health record and medical, electronic medical record. So the history, well, it's not necessarily digital. We're fooling ourselves. A lot of it is text. But nevertheless, that's information. People are now digitizing it. There's also all the prescriptions that I took in the past. There is information about, well, all the medical images, the x-rays, the MRIs, and whatever, you name it. There is also the lab results, all the blood tests and the urine tests and whatever, you name it, that can be added. There's also the genetic information, the microarray data, the SNPs and metabolomics and microbiome can be added. Other sources. We have now all these devices that we have at home for measuring the insulin level, measuring blood pressure and so forth. That can be added. We have these smart watches, different sensors that we wear and use to check our weight and how many steps and whatever can be added. You can also look at the text and extract emotions and add the emotions. So for mental health, you can add it in the DNA. So you can see that you can keep on adding and adding also information where I went. And people have used this to predict whether somebody will get the flu or not. So some work has been done already. But if you collect all this, this is huge, big data. And like the businesses can predict whether you will buy this product or not, and if you don't have it, I'll influence you to buy it. It'll create a need in you. If we were able to put this data all together, can you imagine what we understand about the health in the future of a patient and predict things and improve the quality of life? Unfortunately, there's not a huge investment on this because who would do that? Governments, not big companies who they're investing. These big companies are investing because there's a huge return on investment. Here, who's going to do it? So it's us as a society, we have to consider that. The technology exists. Okay, but of course, there's a huge fear. If you do that, people can attack it to access information that they're not supposed to. There's a lot of, I mean, there's this privacy issue here, security issue. If this kind of data leaks, who knows about the consequences? So this is also possible thanks to not only big data technology, but the AI technology that is capital also within the big data environment. So people, this is where I was supposed to start my lecture for today. People are sending serious warnings about AI, against AI. AI is dangerous. AI not only will replace us, but it's actually an existential threat. And some important people have said that, like, for example, Stephen Hawking. Stephen Hawking said that the biggest existential threat to humankind is AI. He changed his stance afterwards, luckily before he passed away, but actually other people like Elon Musk has said that too. From time to time he adds a little bit more, but don't forget that Elon Musk is the guy who invests in AI companies. He's actually also the founder of Neuralink. Neuralink is a company that is trying to create an interface with the human brain, a chip that you can connect to the neurons in order to record what is happening, the activities that are happening, the thoughts that are happening in the brain, but also to stimulate the brain with things to do. So it's way beyond what people are saying. It's dangerous. So there are kind of contradictions in what people have been saying. People who are basically warning us against AI. After Stephen Hawking actually said his famous warning in an interview with the BBC, he retracted a little bit and he said, actually, the biggest threat is not AI per se, but the use of AI. And for example, if you use AI to help humans or actually replace humans, eventually you'll have robots doing everything. But who can afford these robots? The people who have the means. So the people who have the means will build these factories with robots that will do everything, and we don't do anything anymore. And who will get the profit? Well, those who had the means will get the profit. So the danger is not the AI per se, but the use of AI that will create a bigger chasm between the rich and the poor. So the distribution of wealth in the world will be problematic. That is the biggest threat to humankind. Anyways, I'm not going to dwell too much on this because we don't have time. AI has, well, there are many, many achievements that are worth noting. And this is not just recent. From a long time ago already, for those who remember, in 1997, Deep Blue, a program from IBM, beat Garry Kasparov, master in chess. And now, well, more than, I mean, we're talking about 20 years after, nobody can think that they can beat a computer. Even the chess program on your cell phone is very hard to beat. Checkers was also solved. Not only we beat the best in the world, and this was done here at U of A. Chinook beat Marion Tinsley, the master in checkers. But checkers, the game has been solved. It means that when you start playing a little bit, I can tell you before even you finish the game that I'm going to win as a computer or a draw, but I will not lose. The computer will never lose. Other achievements in 2011, that was a big, big deal. Watson program from IBM also beat the best in Jeopardy. This is the question answering game. That was a big turning point. Other achievements, already in 95, cars were able to drive by themselves. So there was a DARPA challenge, and not only they were, in 95 it was in a closed circuit, but in 2004, 2007, they had even competitions in urban areas. Now, self-driving cars is not far from being achieved completely. So these are huge, huge achievements. Other examples, this is again at U of A, we beat professionals at the poker game. So software using reinforcement learning and deep learning can bluff and can beat professional professional players. So the interesting thing here is that the difference between poker and other games like chess and checkers, you can see the game in front of you. The board is in front of you. You can see the pieces. But with poker, you don't see the cards. So there are many uncertainties. And we are able to beat the humans at that. Okay, so let me tell you a little bit more about something else that was an incredible achievement recently. And this started a few years ago when David Silver, an Australian student, came to U of A to do his PhD with Rich Sutton and Martin Miller. And he was very interested in a game called the Go game. Go is like chess, very popular in Asia. Very simple game. You have two colors and you put these pieces on a board, and you need to basically conquer areas. You have to get more surface than the opponent. And even though it's a very simple game, it was very difficult for computers to beat humans. So even though with chess and checkers we beat the masters at the game, with Go we were not even able to beat kids 9-year-old and 10 or 12-year-old. We couldn't beat them. But David Silver, with the help of Rich Sutton and Martin Miller, they came up with a new strategy that allowed them to beat not the best human, but very good players, so master players. After his PhD, David Silver was hired by a new startup in London called DeepMind. Have you heard of DeepMind? No reaction? Well, DeepMind didn't have a particular product. They were only working on what they call artificial general intelligence. So they are hoping to build a machine that is as intelligent as humans. And the idea is that if that is done, then that machine will solve all the other problems. Okay. So when they hire David Silver, they say, well, just do what you think is interesting in that realm. So he started a team that he called AlphaGo. Does it give you any hints here? Have you heard of AlphaGo? No reaction. So AlphaGo, with the means that DeepMind had, they built way more than what he did when he was at U of A, and his program was able to beat the European champion. And when that happened, that was a big news event. Google acquired DeepMind. And acquired DeepMind at the end of 2013. In the beginning of 2014, Larry Page, one of the co-founders of Google, was interviewed, and he said, the reason why I was particularly interested in that startup called DeepMind, it's because they are able to play games, different games at the same time, and beat the humans. So here's the interesting thing. The program that was doing chess, Deep Blue, the program checker that was playing checkers, the Chinook, they are only specialized in that game. So Deep Blue cannot play checkers and Chinook cannot play chess, okay? They're very, very specialized. Yes, they beat the humans, but the humans are very versatile. They can do many different things at the same time. I can drive a car and I can play chess. I can also do an omelet. I can also invent, I don't know, a new set of glasses. I can do poetry. I can read text. I can do different things. But AI typically, in those programs, they're very specialized in one thing only. But Larry Page was very interested in a program that was playing Atari games. But the same program was able to beat the humans at many Atari games at the same time. So this program was learning, actually with just looking at pixels, and learning how to move the cursor and do better than humans without even understanding the game. The interesting thing as well is that this work was done by a student also from U of A that was hired by DeepMind. DeepMind now is part of Google, and what they did with AlphaGo for the Go game, they actually challenged a world champion. This is Lee Sedol, a Korean guy who has been a world champion for 8 years or something like that, and surprise to everybody, they beat him. So was a catastrophe because in Asia it's a big deal. And now we are talking about jumping from not being able to beat a 9-year-old or 10-year-old kid to beating the world champion. That was a big jump. But the Chinese said, well, the best Go player is from China. That's KG. And then Google said, well, let's play a game. And KG was crushed. And that was a big wake-up call for the rest of the world. And that's what actually made people scared, because they saw that the acceleration was too fast. As I said, from not being able to beat a kid to beating the best of the best in the world. Unfortunately, it didn't just stop there, because what they did to learn how to play this game, they actually fed the computer all the games that they knew about. And the computer learned how to play using machine learning, as I explained to, it learned what action to take in each particular state. But then they did something else. Remember, the company is interested in building general intelligence. So they removed all those examples. Instead, they fed to the machine the rules of the game. This is how you play Go. And then they asked the machine, just play against yourself and learn. And the machine started playing. And at the end of a few hours, it played more games than the humankind has played in 3,000 years, because it can do it fast. This is what they called AlphaGo 0. It means I'm not going to give it any examples. I'm just giving it the rules, and it learns by itself. And AlphaGo 0 beat AlphaGo that beat the humans 1 to 100. I mean 0 to 100 or something like that. So it crushed the AlphaGo completely. AlphaGo 0 crushed AlphaGo. That was a big deal. So in a few days, a few hours, 40 times 24 hours, they played more games than 3,000 years of history of the whole game. That scared people even more. But the funny thing is, it didn't stop there. They said, aha, what if we remove the rules of Go and put the rules of chess? Will it learn how to play chess, not just Go, but also chess at the same time? Let it play against itself how to play chess. And it played against itself, and in few hours, actually 4 hours, it was able to beat the best program. We're not talking about Garry Kasparov and Deep Blue now. We're in 20 years evolution, the best computers that play chess are way better. And this small program in 4 hours learned to play against itself, and it beats the best program. Well, that's very scary indeed. Well, DeepMind didn't stop there. They used the same program, and they taught it how to play StarCraft. So StarCraft is a team game, strategy game, and they created Alpha Star, or from AlphaGo to Alpha Star, and they competed against humans, and they beat the humans. So in a matter of few months, they moved from almost ridiculously playing against a child to not only beating the best, but beating their own program and beating the best chess player and beating the professionals at StarCraft. So it is scary. And people have said, okay, we're doomed. Okay, so the computers will replace us. Really? I showed you some examples with the desert and the dunes and the newts, and I showed you examples with muffins and dogs. We're not there yet. Okay. So yes, we have incredible achievements. Jeopardy, AlphaGo. But let me ask you a question. Do you imagine that a computer robot will be able to pass a university entry exam, let's say by 2025? What do you think? Is it possible? Well, no reaction there. I can tell you that it's already done. Okay, computers can pass the entry exams of many universities, and again, can pass it without any problem. Okay, let's make it more difficult. Who thinks that a computer robot could pass a bar exam to become a lawyer by, let's say, 2030, 10 years from now? Is that possible? Well, that's a program that we already did here at U of A. We have a program that can pass the Japanese bar exam without even knowing Japanese. Okay, so all these are done. And I don't think it'll be a lawyer, but we can use these programs not as a replacement to lawyers, but as a decision support for lawyers to say which rules should apply and what should we do and stuff like that. Let me open the box and show you how Jeopardy, for example, works. It's impressive to watch Watson playing against the humans and answering these questions. But let's see how it works. So in Jeopardy, the questions are actually statements that are not finished, and you need to answer with a question. Okay, so for those who haven't seen Jeopardy, for example, here, Mozart's Last Symphony shares this name, its name with this planet. Okay, so, and you have to answer with a question. Okay, do you know the answer? No. So this is how Jeopardy program, the Watson, sorry, not Jeopardy, Watson would do. I need to find factoids about this context of Mozart and symphonies and planets. Okay, so we are talking about the last symphony that he wrote and the fact that it's known as the name of a planet. So, anyways, I'm gonna skip here. The important keywords here are Mozart, okay, and the last symphony. So what we will do, we'll take these keywords and we'll make them into a query. And if we send them as a query, let's say you using Google as a search engine, you will get resources that talk about Mozart, the last symphony, okay? And I'll choose one of them. Let's say I'll take the Wikipedia page, okay? The Wikipedia page, it has symphony number 41. 41 is not the answer because they're talking about planets. So I will open that page, okay? This is what the computer will do, and we'll read it. Do you think the computer will read that? No, not really. It will try to identify in this web page, and this happens in a fraction of a second, in milliseconds. I will go through this page and I will identify those words that I was looking for: symphony, Mozart, and what was it again? Last. Okay, and and then around in the neighborhood of those words that I highlighted here, now I'm going to do another search about planets, and then planets I will find all these words: Mercury, Venus, Earth, Mars, Jupiter, and so forth. And I will look in the vicinity of these yellow highlighted words. Is there one of these? And indeed, I'll find Jupiter here. So the answer is, what is Jupiter? Okay, and that's how I managed to answer Jeopardy questions very fast, better than the humans. But now that you see inside more, this is a very high level description. And of course, there are some intricate details in there. But once the magic is gone, it's not impressive anymore. Okay, it's not really smart like a human. It is following kind of a process to find the answer very quickly, faster than the humans can remember some of these things. Any questions so far? Okay. So what about, I said exams, entry exams and the bar exam, they have multiple choice questions. They have questions true, false. This is not, Jeopardy is not true, false. Well, it's the same thing that is happening too. If I say true, false, Charlemagne repelled the Magyars. Well, this question, I need to answer true or false. I will transform it into a factoid question, and I will search sources like Wikipedia or whatever, and I will find different answers, and I will add some a function that calculates my confidence for each one of them. So I have the Avars, the Magyars, and the Franks, and then I'll say, no, actually, there's a higher probability that it's not the Magyars that invaded. So I'll say false. Okay, so I have also means, an algorithmic means to answer the true false questions. And there's some more examples in a paper that was published. Any questions? No? I'm trying to
have a quick question.
Sure, go ahead.
In terms of the sort of like the ethics of something like that, how, like, what are the conversations that you folks are having? Because I could see it, like, if the computer could completely pass one of, like, a bar exam or any standardized exam, what are the conversations happening around, you know, even students having like those glasses that have like computers in them?
Yeah. Well, these are very interesting discussions, of course. I want to open this kind of worms here. But yes, if these are in the hands of students trying to pass exams, this is completely unethical. But you can't get hold of these programs today. They're not available. And if they're built, it's not with the intention to build a cheating tool. It is built to show that it's feasible, and this can be used as a decision support system for the professionals who are working in this job. So Watson wasn't built just for the pleasure of beating the humans at Jeopardy. It was built to show actually the technology. They play Jeopardy to show the technology, to try to sell it in other kind of markets. So definitely it's unethical to build it and provide it to people who will cheat and pretend to pass the exam. Well, I mean, I don't want my cat or my dog to become a lawyer and then represent me in a lawsuit somewhere. I wouldn't trust it. So it's not the intention. The intention is to show that this is feasible, and can we use this technology to build a tool that is useful ethically for our society. I'm not going to go in the discussion about whether this is used and how to detect it and all that stuff. It's another issue. Did I answer your question?
Yeah, no, that was very helpful. It's a very fascinating topic, and there's so many different nuances. So yeah, that was really helpful.
Cool, thank you. So I'm going to skip this. This is very quick about the fact that people are now very serious about this, and they after warning us about the danger of AI, actually people are now building institutes and think tanks to cogitate and discuss this issue. But tell the truth, we're still far. I mean, I gave you the example on Tuesday about jokes. Computers are not. They don't necessarily, they don't think beyond a certain limit that we can go beyond. I have this silly example. If I show you this picture and I say, what do you think? What does it represent to you? If I give it to a computer that uses machine learning, the computer will be able to recognize a pencil, which is impressive. It can say, there is a pencil here. So how useful is that? I can have a camera on the glasses of a blind person, and the camera can tell the blind person, I have a glass on the table. There's a pencil here. I mean, it's amazing. It's fantastic. But it can even go beyond. It can even say, oh, there's a pencil in the hand of Osmar because it recognizes my fingerprints that a human being will not be able to do. Okay, so it can go way beyond what a human can do. But actually, the human can do more than that, because if I show this picture to a human being, the human being will not be able to identify me. The human being will be able to identify a finger and a pencil, but can say, well, I see actually a weapon in the hands of a fearsome writer. It's not the kind of imagination. There's no imagination in the computer. Okay, not yet, anyways. So is it paranoia, or is it real, this danger? I showed you the example of the muffins and the dogs last time. But what I want to say is that I'm not going to say it's not danger or there is a danger. There's always a danger in anything we build. There's always a secondary usage. But what I want to say is that this warning is not new. It has been around for a long time. Here's Solomonov, one of the pioneers in AI, who already in the 60s has warned us, and he said, well, if we don't, if we're not careful and we don't put the barriers where we need to, it can overwhelm us, and it can go awry very quickly. So yeah, we have to take it seriously. We should devote some energy and resources to that, but we shouldn't inhibit ourselves from moving forward because there is this potential. Okay? We should be conscious of this potential, but not not shooting ourselves in the foot. That leads us to the singularity. So I'm not sure if this year you talked about the singularity before the AI or not, but basically this idea of singularity is not new. There's this concept of singularity in physics, in astrophysics, and in many other fields. And the technological singularity is basically the time when computers become as intelligent or slightly more intelligent than humans, and they will start driving technology and self-improve themselves. And this is recursively improve themselves, and then we can predict what will happen in the future. That's why we call it singularity. We have no idea what will happen after. It's beyond us. And the question is, will it actually happen? Is it something that is plausible or just philosophical? We think about it, yeah, but it will never happen. Well, let me use a metaphor. So the metaphor is very simple. We have computers today that are very smart, and I showed you some achievements. It's phenomenal. It's amazing. They're very sharp, laser targeting a topic. They're not like humans that are versatile. Even though they beat us in some things, we still beat them overall. So that's fine. So if I have a scale like this and I say, well, we have animals that are intelligent because animals are intelligent. They have emotions, they have goals, and they achieve their goals. Some animals even use tools and things like that. But the animals are not as intelligent as us, the humans. We are the most intelligent animal on the planet. And computers are today less than the animals. So if I put this train, so the scale here is like the railways, and I put the train here, the train is showing the improvement of this AI technology. Eventually, it will not just stop at the train station of the animals, it will reach us. And if it reaches us, nothing says that it cannot go beyond. It can go beyond. But in order to do that, it's not just the intelligence. We have also emotions. We have instincts. We are filled with inconsistencies. We're not always rational, even though it works at the end. Sometimes we act without really reasons. Even if you ask the person, "Why did you do that?" I don't know, just because. Especially when you ask teenagers. We are self-aware. We know that we exist, and we know we want to self-improve. We know that the computer, we can program it. But is it self-aware? Will it be self-aware? These are interesting questions because we don't know how we are self-aware. What makes us self-aware? And maybe that will be reached by computers. But these are all interesting questions. I will pass the next slides. This is just to demonstrate that the computers are, well, I'll just say a few words. A mouse is intelligent. The mouse can cross the river if it needs to survive and the food is on the other side. It can eat things that, well, we talk about the cheese. Cheese is not natural. We invented cheese and the mouse adapted to it and it loves it. The mouse can find resources around it to build its nest. If it's in the field, it will use stuff from the field. If it's in my garage, it will use the stuff in my garage. Everybody knows that the mouse also can memorize the maze and can find its way again once it knows how to reach a goal. It has been demonstrated that the mouse can actually do simple calculation as well. But you can't imagine the mouse looking at the sky and recognizing that those are stars. They're just dots in the sky. I don't know what it is. Does the mouse imagine that these are potential planets where other mice exist? When it looks at the cheese, does it look deeper and imagine that there are proteins that are forming that cheese? When it goes in my garage and nests in my engine, does it understand that that engine is what makes this big metal box move forward and backwards? When it sees this rocket ship going up, does it make this does it imagine that this is going in the sky? And does it make any, I mean, even though it can make some calculations, we can't imagine that the mouse, is I mean, imagining it with abstract formulae and things like that. So we can classify then the intelligence, even though we said the mouse is intelligent, we can classify the intelligence in a scale like this, where the human is intelligence, we call it intelligence 0. And anything that is less intelligent than the human, but still intelligent, is sub-intelligent. But nothing stops us from imagining that there's something that is super intelligence. On the other side of the scale, if we are at 0, there are other things here. So the thing is that can we conceivably think that the mouse could comprehend our degree of intelligence? No, the mouse sees that we are bigger and we are predators. It doesn't know that we have a higher intelligence. And even if it thinks that we are more intelligent than it doesn't know what that intelligence is. It's like when the dog can smell things that we cannot smell. We don't have no idea how to explain that smell of the dog. Anyways, the smell is very easy, but intelligence is even more complicated. So today we can only imagine that there is a possibility of a super intelligence, but we are not in a position to explain what that super intelligence could be and what it can do. Now the question is, how do we get to this? This is now beyond the 0 is the singularity. How can we get to that? Okay, and for me there are 4 paths to the singularity. The first one is helping biology, helping evolution, if we believe in evolution, helping evolution to create natural humans that are more intelligent than the humans that exist today. Okay, that can take time. That can take time, but it's unethical. But believe me, there are people thinking about it. Now, my argument is that an argument that I have is different than this one, but humans haven't evolved a lot. If I take Aristotle, he doesn't know as much as, for example, Einstein. But had he been presented with that knowledge, he would have been as intelligent as Einstein. Both have exactly the same tools, the same brain, biological tools, but they were not confronted with the same knowledge, the same experiments. So the intelligence of this machine called Aristotle and the intelligence of this machine called Einstein is the same, except that they didn't have the same training, the same information, and so forth. The machine itself didn't evolve. Can we help the machine to evolve? We could, but it takes a long time. So the second path is to, what most people think about, is creating an artificial intelligence that exceeds the human intelligence. We saw that the machine itself has evolved significantly. What you have in your cell phone in your pocket is way more powerful than many supercomputers that existed about 10 years ago. So it goes very fast. But while the hardware has evolved and improved quite a bit, software is still way behind. So it'll take time. It is a possible path to the singularity, but I don't think it is the fastest. The other one is the combination of humans and machines. And this has started. So the creation of a human-computer interface, like what Neuralink is trying to do, and many other initiatives as well. And this creates a cybernetic singularity. So it's a singularity not just for a machine, but the human and machine combined. And I'll show you some examples, and I'll convince you that it is possible. And as I said, it has started already. There's a movement called the transhumanism movement that firmly believes in that, and many people are working on that. The fourth path is a path that very few people think about it, but it is also possible because of the Internet of Things that we are having today, so the protocol for machines to communicate, it has been updated relatively recently, IPv6. And IPv6 allows the addresses, each node on this network has to have an address. And now with IPv6, we can have billions of these addresses. Before, IPv4 was limited. And because we have billions, we can have objects that we can connect to the internet, a light bulb, a thermostat, my watch, sensors. And this is what we call the Internet of Things. They collect data, they can exchange, and so forth. From that incredible network of billions of objects that are smart themselves individually, they don't have a big intelligence like a big computer, but they have some smart processor in them. Well, from that combination, an intelligence can arise. We don't know. I mean, it doesn't have to be the intelligence of humans. It's another form of intelligence, and who says that that form of intelligence is not better than ours or superior to some extent? And why I'm saying this is possible is by observing nature. I have a video here, but we don't have the time to watch it. The video basically shows, so they poured concrete in an ant's nest in Africa, and then they dug it to show the connections of these rooms. They have rooms where they store different things. They have rooms where they actually capture other insects, and they have herds of insects inside there that they feed them and eat their excrements or something like that. And they have incredible architecture inside it. And the question is, does one ant understand this and build this, design this architecture? No, it's the collective all put together. So the collective can form a new intelligence that one individual doesn't have. It's a little bit like the neurons, and neurons have some processes. They get signals, and then they decide at one point to send a signal. A neuron alone doesn't do much, but it's putting all the neurons together that creates the intelligence that we have, that we still don't understand, actually. So anyways, these are the three paths. The one that I believe is the fastest is, of course, the one where we're mixing machines and humans, so flesh and mechanics. And often people think, so this is the picture from Star Trek. This is Captain Picard after he was abducted by the Borgs and was assimilated. If you don't know Star Trek, I invite you to go and watch it. It's actually fantastic, from the 90s. So often people think about mechanics added to humans, okay, to build prosthetics. And Patrick Pilarski will talk about the augmentation of the human body with these prosthetics when people lose a limb and stuff like that. But these limbs will be so sophisticated that people will choose to have them because the artificial limb is better than natural limbs, so they may choose to do it. It's not because of an accident, because they want it. And today we have already cyborgs that walk around us. We have artificial hips and knees and artificial eyes and things like that. But the cyborgs, it's not just adding mechanical things to humans. It can be also adding flesh to mechanics. So there is I have another video here, but we don't have the time to watch it. It's an experiment that was demonstrated in the UK, where they used brain cells from the rat, and they connected them in a petri dish, actually, and then they take the signal from that rat, and it is sent from the rat cells, and it's sent through radio frequency to this robot. So they have different robots. They all look the same, but each one is controlled by some cells from a rat, so they have different behaviors. They look like cookie cutters, the same one, but each one is individual. And they are able to make them turn left, right, forward, backwards. So these are the first steps, but soon it'll be way more complicated than that. Okay, that's the rat. So we're getting closer to the mythical characters like the $6 Million Man and the Bionic Woman that we saw in science fiction movies. Actually, science fiction movies give us a lot of ideas for the cybernetics. People often talk about the Terminator, and that's why, oh, it's dangerous and eliminate us. But actually, it's not new. This idea of computers replacing humans has started from the early days of computers. There's an interesting movie that came out in 1969 called Colossus, and they talk about how a computer in the United States and a computer in Russia actually collided together, and they conspired against the humans. So from the early days of computers, people were already panicking about how bad computers could be. But let's talk about the good things. Here's an interesting thing that I'm trying to make the point about cybernetics and why it'll happen, and it is happening today. You know about the cochlear implants. The cochlear implant is more than 100 years already. It's a technology that can send signals to the bone in the back here, and basically that can simulate the bones in the ear, and you can hear sounds. So for people who don't hear properly, we can have a cochlear implant to make them hear. So there's a microphone that gets the signal and then translates it to these signals to the bone. The same idea was used for the eyes recently. So there's a chip, I'll show you a picture. This is a chip that is put on the retina for a patient who lost vision with the deterioration of the retina. And what happens is that they wear glasses. The glasses have cameras. The cameras capture the environment, and the picture is sent by wireless to the chip, and the chip will simulate the optical nerve to make you see something. So the blind will end up seeing. The early experiments, they had 4x4 pixels, and now they're 64 by 64 pixels. And this blind person now can see silhouettes and can see around them. And there are many companies working on this. And here's another company. This is an Australian company. They also do the same thing. This image is becoming like that. So a person who was blind suddenly can see things. It's an incredible improvement. But when you see these pictures, they're pixelized, yeah. They are grayscale, but this is the early days of the digital camera. Digital cameras used to be like that. And very quickly now you have 1,000,000 megapixels. Okay, so this is going to happen. I'm going to skip here very quickly just to show you examples of this. This is from 2011. This is very old, just to make the point. This is a picture taken in Vancouver. Okay, in Vancouver, during the Stanley Cup finals in June of 2011, it was happening in Vancouver, and not everybody could get inside the stadium. They want to watch. So CBC and the city have organized these big screens in the streets to allow people to watch the game while they're not in the stadium, when they're outside. Okay, so here's an example. Okay, you know what happened? Stanley Cup. Well, the Canucks didn't win. They lost, and a riot started, and they started breaking stores and vandalism everywhere. And then the police was asking people to provide their pictures in order to be able to arrest people, that they have proofs and stuff like that. Unbeknownst to many people, actually, the city has installed already cameras everywhere in the city, in many places in the city. This is in 2011. And these cameras are 70,000 by 30,000 pixels. So it's 200,000 megapixels. It's not the normal camera that you use. These are special cameras. And you see this crowd here. I'm talking about 2011, so it's about 10 years ago. Technology is way better today. Do you see that tree here? Do you see the person standing next to the tree? You can't. Okay, so I'm talking about this particular square here. There's a person here. You don't see him, huh? So they think they're hiding in the crowd. You don't see them. Well, I can zoom in. So now do you see that person here? Nah, you don't recognize him yet. So I am going to zoom in. Do you see the person? Now I can see people that are apparently hiding in the crowd. So imagine that capability in that chip on the retina. It's better than the human eye. So if there is a possibility like that, why should I keep my eye? If I can have an eye that can read a newspaper 500 meters away, well, I prefer that eye than this natural eye. Wouldn't you? Maybe not everybody, but a large number of people will choose. That's why I'm saying there will be a choice and people will choose. Those that have the means to access it and the means to pay for it, they will do it. Okay, this is what you would have as a resolution in case you were using a normal camera. This is not a normal camera. This is the normal camera that you have. But these high resolutions are coming very quickly. This is another example of zooming in from a 195 billion pixel camera that is put on the top of a building. This is a few years ago. I mean, the technology is getting better and better, and it's accessible because it's becoming cheaper and cheaper. Okay. So the future is already here. It's just not very evenly distributed, and it'll get there. So here's some examples of what people have done so far for mixing electronics or mechanics to the human being. And this is called body hacking because it's allowed. There are no rules, no controls. People do all sorts of things. So this is biohacking or body hacking. People are putting RFIDs in their bodies. Okay, like here you can see it. It's like a grain of rice. It's an RFID, and they put it inside their skin. And with that, they can identify themselves. They can open the car. They can start the engine of the car. They can start they open the door of the house. And this technology is very cheap and has attracted a lot of attention by many companies and governments. And there are companies in Europe, particularly in Sweden, that offers it to all their employees so that they can be tracked in the company where they walk and which computer they start. So just to log in, you wave your hand and your computer is starting, or you open the door, or you buy things from to pay for them in the distributor, the machine to buy I don't know, a sandwich or a drink. Here are other examples, a little bit ridiculous here. This is the case of teenagers who added underneath their skin here a detector for hotspots, Wi-Fi hotspots, and they added LED lights. So whenever they pass next to a hotspot for Wi-Fi, the light turns on. So they know that they can connect their phones or whatever. Here's another case. This guy actually put in his arm a hard drive to store all the information that his camera that he's wearing is capturing. And nobody can steal this hard drive. It's ridiculous. Of course, you can see it's not even done by a professional doctor. There are things a little bit less intrusive. This is a chip that is printed, so you can tattoo a chip or tattoo a print of a chip. So it's getting there. We are just at the beginning, and very soon you'll see an acceleration when this is affordable and available, and you'll have more and more cyborgs. Okay. Any questions? We're already at 3:30. I can keep on going. I can stop here and let you ask questions. Unless you're so flabbergasted that you can't find your words. Okay. How do we know if a machine is intelligent? We know that we are intelligent, we think. How do we know a machine is intelligent or not intelligent? Well, there is a test that was proposed by Alan Turing in the 50s, 1950 actually, more exactly. You probably know about Alan Turing if you watched the movie about Alan Turing. He's a mathematician in the UK who participated during the Second World War in deciphering the enemy code and build different machines. And after the war, he wrote a book, an essay actually, called Computing Machinery and Intelligence. Can Machines Think? And in that, he explained actually a procedure or a test how to, well, the computers didn't exist then, very few computers existed. Not the computers that we have today, but he was already thinking about this possibility about artificial intelligence, even though the term didn't exist. And he devised this test, and this test is called now the Turing test. Basically, you have a computer or a machine, I mean a machine in general, or a human behind curtains or in the other room, and you have a judge in one room. And they are connected somehow wirelessly or with wires or whatever. And they have a dialogue, question answering. And if the human judge cannot say that whether it is a computer or a human, then if it is a computer, then the computer is smart and intelligent. Does it make sense? Okay. So actually he said that if the machine is able to fool the judge that it is a human for at least 5 minutes, then it's smart. Remember, this was said in 1950, so like 60 years ago. Okay, so people have tried to build such chatbots that you can test, and you need to know whether it is a human or not. And there were competitions created specifically for that, trying to fool computers. One of them is the annual Loebner Prize competition. And so this is a rich guy who offered $100,000 if you manage to build a chatbot that fools humans that it is actually a chatbot, not a human, for at least 5 minutes, then you will win. And for years they were trying, and I'm not going to go into all the examples, but I have examples of chats with some of these winners, and it's really bad. It's not, I mean, very quickly you see that they're not humans until, so many examples here, Cleverbot and so forth, until 2014, one computer was able to fool humans. They thought it was indeed a human, not a machine. But they used tricks because their goal is not to have a conversation. Their goal was simply to cheat and fool the humans. And in this particular case, it was how did they cheat? Basically, well, cheat. They claimed that this is a young boy, 13-year-old boy, so it doesn't know much. It's just a young teenager. And this young boy is from Ukraine, so doesn't know all that. So he may make some wrong sentences. So you're more indulgent for these things, more forgiving. And was having a conversation with humans, and finally, after 5 minutes, they were not sure. They thought it was indeed a little boy, but it was a machine. So they won the $10,000, $100,000. That reminds us, for example, the chatbots that we use today, like Siri and Alexa and Cortana and things like that. Unfortunately, these chatbots are not meant for conversations like humans. They are designed for information retrieval and for responding to some tasks. So you can ask it, where is the University of Alberta, and it'll find the information and it'll bring it back. You can ask it who's the president of the United States, it'll give you back. You can say also, can you buy me such and such? So you give it tasks. Call my brother, or remind me of sending an email or something like that. So they're very limited. We call them slot filling chatbots, because they try to identify the intent that you have, and based on the intent they have a template to follow, whether to reserve a table at the restaurant or something like that. So they don't have a fluent kind of conversation. We're still way behind. They certainly don't have emotions. They don't have empathy. We're not talking about humans anymore here. We're still far away. Yet we have, as I said, we had many achievements. I'm going to skip some of these, trying to see where we get to the end. Actually, I'm at the end here. Let's stop it here and open it again for a chance to ask a question. You're still here, so it seems that you are interested, so that's good.
So I wanted to point out that on Tuesday, we're having a Future and all that jazz recording that takes place at 3:30. So we are going to have a hard stop on the teaching session on Tuesday.
I will do that.
Yeah.
Am I still sharing the screen or not? Yes, I'll stop share. There you go.
Yeah. So any questions?
I just want to make a comment. Like, as you said, you scared us at the end. Like, it is getting way beyond than we thought of at the beginning, actually, of this course. To be honest, like, I didn't have any idea that things are far away that much. But I mean,
you scared?
Yeah, because I mean, before this course, or without this course, I wouldn't have, the chance to look at all of these details and, dig into that point. But I mean, it has been interesting, and you took us far away than we thought. And thank you very much.
Oh, you're welcome. You're welcome. I hope I didn't scare you, but instead gave you motivation to dig deeper and find more about what exists and what you can do.
That's true. You did.
Good.
You opened the windows for things that we didn't know that it exists, and that's very good for sure.
Good. Any other comments or questions?
I have a quick question about the earlier part of the talk. So you're talking about like data with like the medical field and like the privacy issues, and like since you need such a huge amount of like training and testing data, how is that like being worked with to be able to get that data like as of now?
It's very hard. It's very hard because of privacy issues. Those who have the data, hospitals, the government, whatever, they don't want to release it like this because, I mean, the patients haven't officially consented to the use of this data for whatever. The only consent that they gave is an implicit consent. I go to you, doctor, I allow you to use my data to treat me. That's the consent that I'm giving. But I'm not consenting that you share my data about my health to researchers or who knows what to do, I don't know what with it. So technically it's very difficult to get. However, people are getting more and more, I mean, they're realizing the importance of using this data for the common good. I can give you an anecdote. I was working with colleagues about detecting nodules in pulmonary scans. Okay, so they were using, this is a company in China, and they were using computer vision to identify structure in the image, in these CT scans, and identify them as nodules. Unfortunately, using just computer vision techniques, they had many false positives. So many of these structures, they thought they were nodules, and when you present this to a radiologist or a doctor, they're overwhelmed with false positives, so they don't want to use the system anymore. It's too much, it's noisy. So they contacted us to work with them to identify the true nodules from the false positives. And we needed, so we built machine learning techniques to do that. Unfortunately, we needed data. So we are here at U of A. We have a huge university hospital with among the best doctors and researchers in the world, but we can't access to this data. We can't access to CT scans without names. I don't care if it's a female or male or the age or whatever. I just want to know where is the false positives and the true positives. Where did we get the data? We asked our friends in China. Absolutely no problem. Here an email with a bunch of pictures. So what does that tell you? Countries where they don't have this restriction, they have the opportunity to move forward and will be left behind. So many decision makers in Canada and elsewhere are now thinking seriously about how to provide access to the data without jeopardizing the privacy of people. Just this morning, I had a meeting with a new initiative in Montreal funded by the federal government here called DHDP. So this is the Digital Health Discovery Platform. They have about 80-something organizations involved in this initiative. There's $49 million from the federal government. We tried to create a sandbox that stays in the hospital so the data doesn't leave the hospital, but researchers like myself can access the data in a indirect way without accessing the identifiers, and can still try techniques like machine learning. And the goal for them is to come up with new techniques that can be commercialized. So we have startups doing things that can, I mean, it's for the betterment of the healthcare system. But finding the balance is extremely hard. So when I showed you examples that we did here at U of A, it is with researchers at the Cross Cancer Institute. It's with the researchers in pediatrics. It's with the researchers. They have their own data that they collected. In it, we made sure it's, of course, anonymized and all that stuff. But doing it globally and at a larger scale, it's very, very hard because of the issue of privacy that I mentioned. Does it address your question?
Yeah.
These are great questions. This is very important. It's something we have to consider. You can't release data like this because, well, some people want to do good with it and some people may, I don't know what they will do with it. So
does it also like vary depending on what kind of medical data is, like stuff with like maybe like mental health or fertility?
Yes. So the work that I'm doing for depression detection, it's about mental health, and it's often, and I'm looking for text, so things that they write. Accessing that, my gosh, it's very hard. So I can talk to psychologists who have their own data for their own patient, but they are not authorized to share it. In other jurisdictions, they can. India, China, I mean, Africa, there's no issue there. Okay, other questions?
Okay, great. Thanks for another great teaching session. We'll see you all on Tuesday.
Cool.
Okay, great. Thanks.